We are going to look at conjugate acid-base pairs. The Bronson-Lowry definition of an acid is substances that can donate H+. That sounds familiar. Bases are substances that can accept H+. So notice it's broader than the OH- definition. It's something that can accept H+. And what a conjugate acid-base pair is something like this in this equation. We have HCl plus H2O forms H3O plus Cl minus. The HCl and Cl minus are a conjugate acid-base pair. The HCl loses H plus to become Cl minus. The Cl minus could gain H plus to become HCl. The thing that loses the H plus is acting as the acid. The thing that gains H plus, which is a Cl minus here, is acting as the base. H2O is acting as a base because it gains H plus to become H3O plus, and H3O plus is acting as an acid because it loses H plus to become H2O. In this equation, we have H2O plus NH3 forms NH4 plus OH minus. The H2O in this case is acting as an acid because it goes to OH minus. It loses an H and a plus. And the NH3 is acting as a base because it's gaining H plus to become NH4 plus. Or the NH4 plus loses an H plus to become NH3. So what's the difference between an acid and a base? The acid loses H plus and it becomes OH minus, so the base has one less hydrogen and one smaller charge. Okay, just like here, the base has one less hydrogen and one lower charge than the NH4 plus. Okay, notice water acted as a base here and water acted as an acid here. It is amphoteric. It can act as either an acid or a base depending on the situation. We'll see other things doing that as well. Over here we have acetic acid, which is the active ingredient in vinegar. Its conjugate base is over here. What's the difference? This H plus right here. H2O is acting as a base. Here's the acid. What's the difference? It's the extra H plus right here. And here we have H2O acting as an acid. And in this case, what's the difference? The conjugate base has one less H plus, so it's OH minus. And here we have CO3 minus 2 acting as a base. And we have HCO3 right here as the acid. Notice we're writing each reaction is reversible. On one side is usually favored in equilibrium. We're going to take a little bit closer look at that and how to rank these particular things. But these are the conjugate acid-base pairs. Okay, let's go to the second part of this and bring this up here. And we're going to take a look, see if that's going to stick for us. I think that works pretty good. Okay, so what we're going to do is look at a system, and it's a little bit hard to see, but it says draw lines to connect each acid-base pair, label the stronger acid, the stronger base, the weaker acid, and the weaker base, and which of these is favored in equilibrium. So first off, I'm just going to look and say, HCl gets paired up with Cl minus. This is the A for acid. This is the B for base. And NH3 gets paired up with NH4 plus. This is B for base. This is A for acid, the difference being an H plus. All right, so we have them paired up. Now the trick is to figure out what's stronger and what's weaker. So I'm going to compare HCl to the other acid in the equation, NH4 plus. So I'm going to compare these two things, and let's take a look at that. Now with that, I have another chart right here, and this is an acid-base strength chart. Okay, so I'm going to take a look at this right here, and notice it's a ranking of all these things that could take an acid and convert to its conjugate base. How do you convert an acid to its conjugate base? You get rid of the H plus. So So the acids are in the left column. It gets rid of H+. The conjugate bases are here. The strongest acids are toward the top. The strongest bases are toward the bottom. So the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. So we've talked about strong acids as things that completely dissociate. We mentioned that a little bit anyway. And notice the top 6, they completely break up 99+% into ions. So if I have 100 molecules of HClO4, essentially all of them are going to break up into H+ and ClO4-. In fact, these first 6, if we looked at an equilibrium constant value for it, it's going to be very, very large. Okay, but other ones actually have a value and they don't dissociate very much, and they're called weaker acids right here. So let's take a look at this case that we have in this example, and we have HCl compared to NH4+. And I see HCl is way up here. It's in like number 4 over here. It is a strong acid. NH4+ is way down in number 29 right here. So the HCl is stronger than the NH4+. Okay, so I'm going to label this as the stronger acid. This is the weaker acid. What about the Cl- and the NH3? Well, I go way down to number 29 and I see the NH3 way down here. I see the Cl- way up here. Remember, the strongest bases are toward the bottom. So the NH3 is going to be stronger than the Cl- right here. So I'm going to say NH3 is a stronger base and the Cl- is the weaker base. Now notice what happens. The 2 strong things are on one side and the 2 weaker things are on the other side. If you do this right, that will always be the case. The 2 strong on one side, the 2 weaks on the other side. Notice also you have an acid and base over here. What's going to react more forcefully, the 2 strong things or the 2 weak things? Well, the 2 strong things react more forcefully than the 2 weak things by definition. So we say that the products are favored in equilibrium. Okay, let's do another example. I'm going to take acetic acid, combine it with NH3 to form the acetate ion in NH4+. Here's one pairing, acid and base over here. Here's another pairing right here where you have base and you have acid right there. I'm going to look at it and look on my chart. And I don't see that C2H3O2-, but I see this one right here, which is really the same thing. It's this acetate ion. I don't know if I can get this in here. We have 2 carbons, 3 hydrogens, and 2 oxygens. And there's that 1 oxygen attached to the, or the hydrogen attached to the oxygen. That's the hydrogen that's going to peel off here. So sometimes you see this written like this because that's the shape of the molecule. Sometimes you see it as HC2H3O2. But this is the acetate ion that we're talking about with its conjugate base. The other choice, again, is down here, NH4+ and NH3. Notice the acetate ion is going to be above the NH4+, so we're going to call it the stronger acid compared to this. And notice the NH3 down here is going to be lower than the acetate ion, so we are going to call this the stronger base. Stronger acid, stronger base on the same side. The reaction is going to go to the right. Products are favored. Just a couple reminders. Both strongers are going to be on the same side if you're doing this right. Both weakers will be on the opposite side. You should get 1 acid and 1 base on each side, and the side opposite the strongers is always going to be favored. What's this thing we talked about, the strong acids on the top? And even though acetic acid is not a strong acid, it is still stronger than the NH4 plus. So the SA refers to stronger acid, not necessarily a strong acid. SB refers to the stronger base, not necessarily a strong base. Try the problems 9 through 11 using this information.